Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will discuss the types of DC generators or types of DC machines. There are two types of DC machines, separately excited DC generator and self-excited DC generator. In separately excited DC generator, the field winding and armature windings, they are separate and they are mutually connected with each other, which you can see in this figure. So this is the circuit of the field winding, and we are separately exciting the field winding, and this armature winding is separate, and this armature will be rotated in the magnetic field which is produced in this field winding excitation, and that magnetic field is actually linking with the armature, and when mechanical energy is supplied to this armature, EMF is induced across these armature windings, and that electrical energy is supplied to the external load. So this is one type. In second type of DC generators, uh, the field and armature windings are mutually connected with each other. And this type of DC generator is called self-excited DC generator or self-excited DC machine. So the armature and field windings are connected with each other, and they can be connected either in parallel or in series. If the two windings are connected in parallel, then that generator is called as shunt wound self-excited DC generator, and this is called series wound self-excited DC generator, because here the armature winding and field windings are connected in series with each other, and this is the load. In series wound DC generator, we have to use less number of turns and thick wires of the field winding, and the field winding is also uh, done using less number of turns, right? So this type of series wound DC generator is less used. Its use is less in the industry, but shunt wound DC generator is used mostly. So their properties will be discussed in the coming lectures. And The third type of the self-excited DC generator is compound wound. And in compound wound DC generator, there are two field windings. One field winding is connected in parallel with the armature, and the other field winding is connected in series with the armature, which you can observe in this figure. So this is called a short shunt compound wound DC generator, right? Another type of compound wound DC generator is long shunt, and in this type, one armature winding uh, is connected with one field winding, and another field winding is connected in parallel with the series combination of these two windings. So which you can see in this figure. And again, we have two field windings. This is F1 and F2, and armature are connected in series, and their combination is connected in parallel with F1, and this is the external load. So this is called long shunt compound wound DC generator. Now I will solve some numerical problems, and we will have a better understanding of the self-excited DC generator circuit. In this problem, we have to evaluate the generated EMF across the armature winding of the DC generator, and we are given a load which is operating at 230 volts, and the field winding has a 50 ohm resistance, armature winding has 0.03 ohm resistance. The load current is given as 450 amperes, and first we will evaluate this current which is flowing through this shunt field winding, right? So this is 230 volts, and if we divide this 230 volts by 50 ohms, then we will evaluate this current which is going in this branch in this field winding. So I shunt is equal to 230 by 50, so it is equal to 4.6 amperes. Load current is equal to 450 amperes. So the armature current will be equal to 450 plus 4.6, so 450 4.6 amperes. And the voltage drop across the armature winding is equal to armature current multiplied by the armature resistance, which is equal to 0.03 ohms. So this is equal to 13.6 volts. Now the generated EMF will be equal to IARA plus 230, right? V plus IARA. So 230 plus 13.6 is equal to 243.6 volt. So that was a very simple example on shunt bound DC generator. Let's solve another problem. And in this problem, we are given short shunt compound wound DC generator. So this is the armature winding, and we have to evaluate the induced EMF or the generated EMF across the armature, and we have to evaluate the armature current. Right. So we are given this series field winding as 0.3 ohm, and this shunt field winding has 200 ohms resistance, and this is the terminal voltage which is equal to 220 volts, and these voltages are available across the load impedance. So Vs will be equal to 0.3 multiplied by 30, right? So this is the voltage drop across this series winding. So this is equal to 9 volts, and the voltage across this armature winding is equal to 220 volts plus this 9 volts, right? So this winding and this load impedance are connected in series with each other. So the voltage across the armature winding will be equal to 220 plus 9 volts. So this is equal to 229 volts. And let's evaluate the shunt current. So this shunt current is equal to this voltage 229 volts divided by 200 ohms. So this is equal to 1.145 amperes. Now armature current is equal to series current plus shunt current, and that is equal to 31.145 amperes. This is the armature current. Now the armature resistance is given as 0.05 ohms. So IARA is the armature winding drop, and that is equal to 1.56 volts. Now the voltage drop across two carbon brushes is given as 2 volts. So the generated EMF will be equal to uh, this 229 volts, right? Plus the brush drop plus IARA, right? So this is 229 plus brush drop plus IARA. So that is equal to 232.56 volts. So that is the generated EMF across this armature winding of the compound wound DC generator. Now we will discuss the mathematical formula of EMF equation of DC generator, and we are given phi as flux per pole, right? So if we are given flux as 50 Webers, for example, and total number of poles are 4, then the total flux will be equal to 50 multiplied by 4. So phi is actually the flux per pole, which is equal to 50 Weber, for example. So phi will be equal to the flux per pole. So total flux will be equal to phi multiplied by total number of poles. So that will be equal to P phi. Now Z is equal to total number of armature conductors, and that is equal to number of slots multiplied by number of conductors per slot. If we have a single layer winding, then Z will be equal to total number of slots. If we have multi-layer winding, for example, two-layer winding, then Z will be equal to number of slots multiplied by 2. If we have three-layer winding, then Z will be equal to number of slots multiplied by 3, and so on. So P is the number of poles, A is the number of parallel paths, right? So if we have um, a wave wound DC generator, then number of parallel paths will be equal to 2. If we have a lap wound DC generator, then A will be equal to the number of poles P, which we also discussed in our previous lecture. N is the armature rotation in RPM, and E is the EMF induced in parallel path. Average EMF generated per conductor is equal to d phi by dt according to Faraday's law, right? So according to Faraday's law, induced EMF is equal to d phi by dt, and its unit is volts. So flux per pole in one revolution is equal to P phi, right? Flux per pole is equal to phi, but total flux for P poles is equal to P multiplied by phi. So our d phi will be equal to P phi, and this is the flux per conductor, right? So when we have multiple conductors, then we have to multiply this P phi with the total number of conductors. And let's suppose N is the number of revolutions per minute, right? N is RPM. So number of revolutions per second will be equal to N over 60. So These are the number of revolutions per second, right? So time is coming in the denominator. So if we take time to the numerator, then we have to take the reciprocal of this term. So that will be equal to 60 over n. So in this case, dt will be equal to 60 over n, right? So this is our d phi, this is our dt. So according to Faraday's law, d phi by dt will be equal to p phi n over 60 per conductor. So if you have problems understanding how we have estimated this dt, then I have another mechanism to understand this expression. So if we have n revolutions per minute of a DC generator, so the shaft of the DC generator is rotating at angular speed of n revolutions per minute, right? N revolutions per minute, RPM. So it means time for n revolutions is equal to 1 minute or 60 seconds. And time for one revolution will be equal to 60 over n. So it means time will be equal to 60 over n. So that's why we have written dt equal to 60 over n. So I think now it is clear. And let's put these two values in this Faraday's equation. So dy by dt is equal to EMF, which is equal to p phi n over 60 per conductor. Number of conductors in one parallel path is equal to z over a. So total EMF will be equal to p phi n divided by 60 multiplied by z over a. So if we have a lap winding, then we will use this expression. And if we have wave winding, then the number of parallel paths will be equal to 2. So in that case, total EMF will be equal to p phi n over 60 multiplied by z over 2. So the important thing in this discussion is that we are considering number of conductors in one parallel path, right? So this is very important to understand this aspect, because in our previous lecture, I will recall that the induced EMF will be depending on the number of conductors in one parallel path, right? So if, for example, this conductor is inducing an EMF of 1 volt, then this conductor will also be inducing EMF of 1 volt, similarly 1 volt and 1 volt. So total volts will be equal to 4. Similarly, 4 volts will be induced by this parallel path. Similarly, 4 volts will be induced by this parallel path, and so on. So it is important that we consider number of conductors in one parallel path. If we consider total number of conductors, then total number of conductors are equal to 16. But the total induced EMF will be the one which is given by the series combination of these four conductors, right? These four conductors are connected in parallel. So the induced EMF due to these four conductors will also be equal to the induced EMF due to these four conductors. So number of conductors in one parallel path will be giving us the total induced EMF. So that's why we have to consider number of conductors in one parallel path. So that's why we have used Z over A over here, right? So for lap winding, induced EMF will be equal to this expression, and for wave winding, induced EMF will be equal to this expression. And we know that for lap winding, number of parallel path is equal to the number of poles. So we can cancel out this P and A. So we will get N phi Z divided by 60 as the induced EMF for lap winding. And for wave winding, this will be the expression. So let's solve a numerical problem, and this numerical problem is very easy, but it is a comprehensive numerical problem because it will consider many terms which have to be evaluated, right? So in this circuit, we are given four number of poles of this DC generator. The voltage drop across one brush is equal to 1 volt. So the voltage drop across two brushes will be equal to 2 volts. Induced EMF is the quantity which has to be evaluated, and flux per pole is equal to 0.02 Webers. RPM is equal to 1200, and finally we have to evaluate the total number of conductors which are present in this DC machine. Okay, so let's first consider the data which is given to us. This is a shunt field winding whose resistance is equal to 200 ohms. This is series field winding whose resistance is 0.04 ohms. The resistance of this armature winding is equal to 0.03 ohms. 500 volts are the terminal voltage which are available at the load, and 50 kilowatt is the load, right? So we can evaluate the load current, right? So we can divide 500, uh, we can divide 25 kilowatt with this 500, right? So I will be equal to 25 kilowatt divided by 500. So current is equal to 50 ampere is the load current. Similarly, the shunt current is equal to 500 divided by 200. So that is equal to 2.5 amperes. Now this armature current will be equal to 52.5 amperes. Okay. So this resistance is 0.04 ohms. So series field drop is equal to 52.5 multiplied by 0.04. So this is equal to 2.1 volts. This is the voltage drop across this series field winding. Similarly, the armature winding drop is equal to 52.5 multiplied by 0.03, and that will be equal to 1.575 volts. Similarly, brush drop is equal to 2 volts. The total induced EMF will be equal to this 500 plus this drop plus brush drop plus this armature winding drop. So after adding all these voltage drops, we will come up to a value of 505.67 volts, which is generated across the armature winding. Now EMF is equal to N phi G divided by 60 multiplied by P divided by A. So 505.67 will be equal to, this is RPM 1200. This is flux per pole. These are the total number of conductors. This is 60. This is the number of poles, and these are the number of parallel paths. In this problem, we are given the DC generator as a lap wound DC generator. So we have to consider number of parallel paths equal to the number of poles. So by solving this equation, Z is evaluated to be 1264. So these are the total number of conductors which are present in this armature winding, right, of this DC generator. So that is all about our today's lecture, and I hope you have quite understood the types of DC generators and you have understood how to solve the DC generator problems. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.